Hi, we are Samir and Christian, and this is our EE327 project, which is the embedded blood pressure monitor. To give a quick recap for our presentation last time, we want to create an embedded blood pressure monitoring system that will have fully autonomous pumping and deflating of the cuff that will be used to assess the blood pressure. The cuff will have an accelerometer attached as well, and this accelerometer will be used to reset the entire system and deflate the cuff if there's substantial motion artifact in the signal. This is because motion can severely reduce the quality of a blood pressure measurement. So we want to provide a method for preventing that. Additionally, systolic and diastolic blood pressure will be calculated by applying a digital filter to the pressure signal and then assessing the Kara cuff sounds. Additionally, the cuff will be controlled from a website, and all of the outputs will be sent to that website and will be stored in a data log for users to check previous measurements as well. The cuff will also need to be low power because we need to run it from a battery. So we did change our design a little bit from our last presentation. So originally we were using a solenoid valve to allow for a really fast deflation of the cuff. And we had another mechanical valve that was used for slow deflation of the cuff. The problem with this was that the solenoid valve and the brass valve were actually like really big, so they wouldn't really fit onto a cuff. So instead, we're actually like 3D printed and mechanically designed a screw that has an O-ring attached to it. And that screw could be screwed in to prevent air leakage, and it could be screwed out by a motor. And this would allow for fast deflation in the case of there being too much acceleration going on in the measurement, or if a user chooses to stop the actual measurement from taking place. Additionally, we also created our PCB, which is shown on the right. So we have like about 5 buttons total. 3 of them will be used to actually control the device, and then 2 of them will be used to reset the ESP and put it into downloading mode. And then we have about 5 LEDs to actually indicate the status of the device as well. The PCB design was a bit more challenging than we expected because we had to make a lot of custom libraries, and this could also present a potential failure mode next week if some of these custom libraries were not designed well. As for the firmware, we've made some pretty good progress. So shown on the left is the raw pressure signal, and you can actually see the bumps on the pressure signal. That's actually the Kara sounds that we want to assess. So after we apply our digital filter, we get the image that's shown on the right that shows those oscillations. And we use MATLAB to just like do some minor peak picking to actually measure these different oscillations and use that to calculate the mean arterial blood pressure. And this was actually a little bit easier than expected. The pressure readings were really clean on the ESP32, and applying the digital filter was relatively straightforward. And reversing things like the phase shift and transient response were also easier than expected. We are still having some issues with the peak finding itself in C++, mostly because there's not as much like built-in libraries as there are in things like MATLAB and Python. So right now our firmware is reading a mean arterial pressure of about 110, whereas when we manually calculate it on MATLAB, it should be closer to 100. So this has been a bit more difficult than expected. Additionally, on the firmware side, we have our accelerometer input interrupt working as well, and as well as our pressure feedback loop with pumping working as well. But we just need to calibrate that a little bit more on when we actually get our PCB. And this has been a bit easier than expected. So here's our mechanical design. So shown on the left is a housing of all of the components, and that's going to be placed on the cuff. So we have the motor used to control the screw in the top left. We have the valve in the top right. The air pump goes on the bottom right, and our PCB is kind of sitting on a shelf that's a bit elevated in the bottom left. And directly underneath that shelf is where the battery is going to be housed. And then shown on the right is kind of like what we've been using so far, showing the valve that's been epoxied to the hose of the cuff, and it's connected to the air pump and the motor and the screw as well. The mechanical design has given us quite a bit of challenges and cost a lot of our time, mostly because designing the fittings were really hard to prevent air leakage and making sure the screw is actually screwing in tightly and preventing air from leaking too much.
Okay, so for the Wi-Fi and website part of the project, so our design is going to feature components that allow the user to start and stop the cuff directly through the website by clicking. And then it's also going to enable them to save blood pressure measurements over time and show real-time measurements taken by the pressure sensor and rock cough sounds. So the plan is basically to employ or like host a website on an ESP Connect from a browser through WebSocket connection, which is kind of the same thing that we did in EE326 with the ESP32. So the idea is to employ a similar design strategy. And right now we're currently looking for advice from groups who are maybe employing the same sort of architecture for their Wi-Fi and website. So yeah, that pretty much summarizes what we're doing for the Wi-Fi and website. And then one thing we learned so far in this stage of the design is for the digital filter application in the hardware, there's actually a nuance in the dimensionality of the filter and transient responses. So higher order filtering corrupts larger amounts of data by introducing transients, which means that sometimes we need to allow wider transition bands to reduce order. And it also means that we need to use asymmetric attenuations to reduce order in our bandpass filtering and accept more ripple in the pass band. Another thing that we need to, or that we have learned so far is about reversing phase effects. So we're able to use MATLAB to test using sine waves of the frequencies that we know for FIR filters. And then, so for the interviews that we conducted after the first round of interviews, so the feedback that we got is that the usage seems a bit complex. How do you plan to ensure that the system remains user-friendly, especially for elderly or technologically less savvy users? So to be able to increase the accessibility for patients of all ages, especially older patients who likely struggle or need to monitor their blood pressure more actively, we have decided to simplify the user interface so that this critical market will be able to use the product efficiently and easily. And the other feedback that we got was that pumping feels it feels a bit tighter, more painful than the doctor's office, which is something that we need to work on because we obviously want our product to be like a comfortable and safe experience for everyone. So we figured we can adjust this in a couple of ways by reducing the maximum pressure allowed in the pressure feedback loop. But this has a drawback of potentially causing the loss of useful data, but we'll have to see and play around with that. And then also we need to allow air to leak faster, which again may cause the loss or may corrupt some of the data that we're looking to collect. And then pumping air faster so that the tightness lasts for a shorter duration is a solution that has no data loss. So these are all options that we're looking at going forward. And then questions that we have for other designers and classmates is, does this system seem overly complicated for users to use and understand? Or does everything make sense to like the average person who's going to be using this? And then any thoughts on how to reduce the size of the housing for like the PCB and the other hardware? Yeah, and that concludes our presentation for presentation 2. Thank you so much and have a great weekend.